This is SpaceTime, Series 27, Episode 19, for broadcast on the 12th of February 2024. Coming up on SpaceTime, astronomers discover a surprise in a Death Star-shaped moon, Juno's latest spectacular close flyby of the volcanic world of Io, and new revelations prove organic compounds in asteroids can be formed in colder regions of space. All that and more coming up on SpaceTime.
Welcome to Space Time with Stuart Gary.
Astronomers have discovered a young subsurface liquid water ocean below the icy crust of Saturn's tiny moon Mimas. Until now, Mimas's biggest claim to fame was the huge impact crater in its northern hemisphere, which gave the little moon the appearance of the infamous Death Star in the movie Star Wars. Now, a report in the journal Nature claims a review of data from NASA's Cassini mission indicates the 400-kilometre wide moon contains a global subsurface ocean beneath its frozen crust. The data suggests this underground ocean is still very young by geological standards, just 5 to 15 million years old. The study's lead author, Valérie Léni from the Observatoire de Paris, says the astonishing discovery makes Mimas a prime target for studying the origins of life in our solar system. The moon's heavily cratered surface gave no hint of the hidden ocean beneath. The discovery adds Mimas to the exclusive club of moons in our solar system that are now known to have internal oceans, including Saturn's ice moon Enceladus and the Jovian Galileo moons Europa, Ganymede and Callisto. But the unique difference here is the remarkably young age of Mimas's ocean. The young age has been determined through detailed analyses of Mimas's tidal interactions with Saturn. The discovery of an unexpected irregularity in Mimas's orbit suggests that the ocean formed very recently. As a result, Mimas provides a unique window into the very early stages of ocean formation and the potential for life to emerge. You see, here on Earth, wherever scientists find water, they find life. This is SpaceTime. Still to come, Juno's latest spectacular close flyby of the volcanic world of Io, and confirmation that organic compounds found in asteroids can be formed in cold regions of space. All that and more still to come on SpaceTime. NASA's Juno spacecraft has just completed its second close flyby of the volcanic Jovian moon Io, revealing stunning erupting volcanoes, blasting iridescent blue ejecta deep into a velvet black sky. It was the second close encounter with this violent world in a row, the other being Juno's previous orbit in December. And like the December encounter, Juno swooped down to within 1,500 kilometres of the molten rock and sulphur-covered moon. Io is the most volcanically active place in the solar system. It's a world where instead of weather reports, you'd have geoscience reports, with fresh volcanic activity in the north, mountain forming in the east, and new lava lakes forming in the southwest. Juno is studying the 3,360-kilometre wide world and its pot-marked surface to determine if Io's active volcanoes are powered by a global magma ocean beneath its crust. Based on current models, scientists believe this magma ocean results from gravitational tidal forces generated as Io orbits Jupiter and is constantly being stretched and crushed by the gas giant's overwhelming gravitational pull. Then there's the pull of the other Galilean Jovian moons as Io undertakes its orbit. All this causes what's known as geological flexing, and that results in a buildup of heat which causes rocks in the moon's interior to melt. It's actually very similar to what Europa and the other icy moons are understood to be experiencing, where tidal flexing leads to hydrothermal activity in the core mantle boundary region, melting the rock-solid water ice into liquid to form a subsurface ocean. Io is the fourth largest moon in our solar system and is slightly bigger than Earth's moon. Io's volcanism is responsible for many of its unique features. Its volcanic plumes and lava flows produce large crustal changes and paint the surface in various subtle shades of yellow, red, white, black and green. Arriving in the Jovian system in 2016, Juno is the first mission to study Jupiter up close from orbit since the Galileo spacecraft studied the gas giant and its satellites between 1995 and 2003. Juno has been looking deep below Jupiter's dense clouds to investigate the planet's magnetic field, its composition, and its structure. This data is helping scientists address serious questions about how Jupiter formed, and for that matter, the origins of our solar system. See, as well as being the biggest planet in the solar system, Jupiter is also believed to be the oldest planet, having formed just 1 million years after the Sun and roughly 50 million years before the Earth. Before Juno arrived, most scientists proposed one of two scenarios for the formation of Jupiter. Now, if the planet accreted first as a solid body, it would have consisted of a dense core, a surrounding layer of fluid metallic hydrogen with some helium and extending outwards to about 80% of the radius of the planet. And then there's an outer layer of atmosphere consisting primarily of molecular hydrogen. Now, alternatively, if the planet collapsed directly from the gaseous protoplanetary disk, which formed the Sun, it was expected to completely lack a core, consisting instead of a denser and denser fluid, predominantly molecular and metallic hydrogen, all the way to the centre. However, the data from the Juno mission shows that Jupiter actually has a diffuse core that mixes into the mantle, extending for about 30 to 50% of the planet's radius, and comprising heavy elements with a combined mass 7 to 25 times that of the Earth. This mixing process could have arisen during its formation, while the planet accreted solids and gases from the surrounding nebula. Alternatively, it could have been caused by the impact of a planet of about 10 Earth masses a few million years after Jupiter's formation, which would have disrupted an originally solid Jovian core. Outside the layer of metallic hydrogen lies a transparent interior atmosphere of hydrogen. At this depth, the pressure and temperature are well above that for molecular hydrogen. In this state, there are no distinct liquid and gas phases. Instead, the hydrogen is said to be in a supercritical fluid state. The hydrogen and helium gas extending downwards from the cloud layer gradually transitions into a liquid in deeper layers, possibly resembling something akin to an ocean of liquid hydrogen and other supercritical fluids. Physically, the gas simply becomes hotter and denser as the depth increases. Since 2021, Juno has been on its extended mission phase, where it's been making flybys of some of Jupiter's largest moons, including Ganymede, Europa, and now Io. This SpaceTime. Still to come, confirmation that organic compounds in asteroids can be formed in colder regions between the stars. And the asteroid that impacted near Berlin identified as a rare orbrite. All that and more still to come on SpaceTime. A new study has confirmed that some organic compounds, including those discovered inside asteroids, may have originated in cold interstellar space environments. Until now, organic compounds were thought to have formed in hot regions near stars. The new findings, reported in the journal Science, have opened fresh possibilities for studying life beyond Earth. The study has been analysing organic compounds, known as polycyclic aromatic hydrocarbons, or PAHs. Polycyclic aromatic hydrocarbons are organic compounds made up of carbon and hydrogen that are common on Earth but are also found in celestial bodies like asteroids and meteors. The authors had been looking for samples from two different asteroids. The asteroid Ryugu, a 900-metre-wide potentially hazardous near-Earth asteroid belonging to the Apollo group, which was visited by the Japanese Aerospace Exploration Agency's Hayabusa 2 sample return mission in 2018. And the Murchison meteorite, which fell to Earth near the Victorian rural township of Murchison back on September the 28th, 1969. Two of the study's authors, Letty Grice and Alex Holman from Curtin University's WA Organic and Isotopic Geochemistry Centre, had performed controlled experiments on Australian plants, which were then isotopically compared to PAHs from both fragments of Ryugu and Murchison. They were looking at the bonds between light and heavy carbon isotopes to reveal the temperature at which they were formed. And they found that some polycyclic aromatic hydrocarbons from both Ryugu and Murchison were found to have had different characteristics. The smaller ones likely formed in cold outer space, an interstellar environment, while bigger ones probably formed in warmer environments like near a star or inside a celestial body. Holman says understanding the isotopic composition of polycyclic aromatic hydrocarbons helps unravel conditions and environments in which these molecules were created, and that offers insights into the history and chemistry of celestial bodies like asteroids and meteors. Grice says the findings provide new insights into how organic compounds form beyond the Earth and where in space they're likely to come from.
Quite a few years ago, we did a series of burn experiments with Australian plants where we actually burn the plants and collect the polycyclic aromatic hydrocarbons which have been formed on land to use as a comparison of a terrestrial Earth source for these polycyclic aromatic hydrocarbons. And they were measured alongside the PAHs from the asteroids and the Murchison meteorite sample to confirm that the source of the pH is in the asteroid, and as a comparison of like temperature associated with combustion of plant materials that was used as a reference point, I would say, to compare the other pHs in the asteroid. So we provided quite important information in terms of what the isotopes would be for those PAHs formed on land.
Tell me about PAHs.
PAHs are very common organic molecules because they're very stable and easily formed by a variety of different processes. On Earth, they're normally formed in high-temperature processes, for example, the combustion of plant material, and also in other areas such as hydrothermal high-temperature vents under the ocean, like in deep-sea hydrothermal vents. Also in the formation of oil and gas under high temperature and pressure, they can be formed. In space, these are generally considered to be formed in, again, high-temperature processes, such as the areas surrounding stars at thousands of degrees Celsius, but it was also has been theorized that they could be formed under low temperature processes within the interstellar medium between stars, but this had never been confirmed experimentally, and that's what this work was designed to achieve.
Was it able to achieve that?
Yes, it was. The samples that were brought back from Ryugu were subjected to a very advanced analysis of the distribution of isotopes in the PAHs, the light and heavy isotopes of carbon, and how they're bonded together using the advanced instrumentation available at Caltech, where the study was based. And these were able to determine the temperature that the PAHs were formed in, and they did find that certain PAHs in Ryugu and Murchison were formed at low temperature.
What processes in low temperature would do that?
Ultraviolet radiation.
And shock waves as well.
Yeah.
Let's go back to the work you guys did to establish the PAHs, the organics that you burnt to achieve that.
These are just pieces of canvas from leaf litter and wood particularly. So just like you would do with a wood fire stove, you burn and then the PAHs are actually formed through the combustion process. The isotopic signal of those fragments reflect the type of plant that's being burnt. So the carbon-13, carbon-12 would reflect the type of plant material. So, for example, if there's a tree, like a temperate tree, such as a eucalyptus, it uses a particular pathway for photosynthesis compared to something like Simifex grass, which uses a different pathway because it's from a very hot environment, and therefore these different plant types fractionate the carbon-13, carbon-12 of the CO2 taken in differently, and that is reflected also in the PAHs that are emitted from the combustion process.
The other importance of these burn experiments we did is were done in a controlled chamber, and the temperature of the burn was very precisely monitored. So we were able to provide a sample of PAHs that we could say were produced at this temperature, at these high temperatures. So that gave the researchers at Caltech like a known point to compare their samples against, to compare where these ones from the asteroid and the Murchison meteorite formed at high or low temperatures, because they have these known high temperature PAHs to compare against.
Mm-hmm.
Were you informed whether or not both Ryugu and Murchison had the same isotopic signatures?
The results from Ryugu and Murchison, some of the PAHs were found to have been formed at the low temperatures that they were theorizing, but others were found to be formed at high temperatures.
Yeah, most of from the ash of the plant is a little bit different to the Ryugu and the Murchison. So there is quite a distinct difference between them.
Tell me about Curtin's Organic and Isotopic Geochemistry Centre.
I'm actually a laureate fellow who investigates organic in very ancient fossils, so in soft tissue, organic from the original organisms, so like the different types of natural product precursors which are preserved in soft tissue, These can be from modern right through to about 600 million years old. So I'm looking at exceptionally well-preserved fossils in geological samples through that program, and we actually make fossils in the laboratory using microbial mats and actually make fossilized material as well. So we're really understanding the processes of different modes of fossilization in geological record. We also work on mass extinction events. So the big 5 extinction events in geological history, including the largest, the Permian-Triassic extinction 252 million years ago. We look at the organics in rocks over time and track changes in the environment and changes in the ocean and atmosphere by using isotopes and organics in the rock. And we've worked on the Chicxulub impact crater from the Gulf of Mexico. We have the core material here we've published looking at what happened within a day after the impact at Chicxulub and how quickly microbial life and life recovered after that event.
Does the iridium line from Chicxulub, from the impact, does it change much in its chemical signature?
Actually, it's not seen all around the world. We're actually going to be working on samples from New Zealand shortly, and it'll be interesting to see whether there's actually an iridium layer there, because that's never really been investigated. So that's further away from the Chicxulub site.
Is there one in Australia?
No, I think largely because the deposits that would be spanning that interval need to involve ocean drilling projects and drilling deep sea, and places where likely it might be is Lord Howe Rise or the Great Australian Bight, where we would perhaps span into that interval. So it's more accessibility to getting samples is the biggest issue in Australia.
Your research has also looked at more recent plants. Tell me about that.
We've actually developed the technique to be able to capture volatile organic compounds from combustion experiments with controlled burns and determine the origin of those organics. So, for example, we can take atmospheric emissions, and actually we've developed a technique where you can actually collect those organics onto a resin and then analytically desorb and measure the composition and the isotopic composition, which is not an easy task.
And there you heard Clitty Grice and Alex Holman from Curtin University's WA Organic and Isotope Geochemistry Centre. And this is SpaceTime. Still to come, the asteroid that impacted near Berlin last week identified as a rare Albright, and later in the science report, paleontologists have uncovered the fossilised remains of a new species of pterosaur on the Isle of Skye. All that and more still to come on SpaceTime. Scientists have identified fragments of an asteroid that crashed to Earth near Berlin last month. The findings by researchers with the Museum für Erdkunde show the space rock to have the mineralogy and chemical composition of an Albright type of chondrite. The results are based on an initial examination using an electron beam microprobe. The findings match observations of the fireball's colour made by astronomers who described it as it streaked through the atmosphere. Astronomers knew it was coming because they detected the metre-wide asteroid just 3 hours prior to its atmospheric entry, cataloguing it as 2024 BX1. BX1 was first spotted and then tracked by the Konkoly Observatory in Hungary. That data was then fed to NASA's Scout and ESA's Meerkat Asteroid Guard impact hazard assessment systems, which then predicted its trajectory and confirmed that it definitely was an Earth impactor. Scientists and meteorite hunters then followed its progress during its entry phase and calculated its likely impact location, adjusting for strong winds. In fact, many people in Berlin and across Central Europe were also able to witness the fireball, and many of them filmed it. After breaking up in flight, small fragments eventually made their way to the ground west of Berlin. Peter Jeniskens from the SETI Institute says the meteorites were difficult to identify because from a distance they look like any other rock on Earth. Albrights look more like grey granite. They consist primarily of magnesium silicates and statite and forsterite. Unlike other meteorites, which usually have a thin crust of black glass from atmospheric heat, these meteorites have a mostly translucent glass crust. The name Albright comes from the village of Aubries in France, where a similar meteorite fell to Earth back in September 1836. Only 8 asteroids have ever been detected before their impact with Earth's atmosphere. The first of these discoveries took place in 2008, and 4 were discovered in just the last 2 years. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study by the Royal Society Open Science says more needs to be done to stop animal cruelty during transport. Dozens, maybe hundreds of animal deaths have been recorded on board a live export ship carrying more than 15,000 animals, which is now making its way back to Fremantle in Western Australia after being left adrift for over a month. The federal government took until last week to decide what to do with the ship, which had been left stationary in heatwave conditions because of attacks by Yemen's Islamic Houthi terrorists in the Red Sea. The problem is the Albanese Labor government has failed to keep its election promise to ban the inhumane practice of live animal exports. Now, a report in the Journal of the Royal Society Open Science shows that British and Canadian scientists studying livestock transportation regulations in 5 English-speaking Western jurisdictions, including Australia, Canada, New Zealand, the EU and the United States, have found that existing laws are simply too vague or insufficient to prevent animal cruelty. The authors examined evidence relating to 4 major risk factors, including journey duration and space allowances, finding regulations simply failed to adequately protect the animals. They say increased inspections and training for transporters needs to be substantially improved for the sake of animal welfare. Of course, the Albanese government could stop all this by simply keeping its election promise and banning the transport of live animals altogether. A new study conducted at the Westmead Institute for Medical Research has solved a complication that could occur following an experimental procedure to repair damaged heart muscles. Right now, when a heart muscle is repaired using stem cells, there is a risk of developing an abnormal heartbeat. Now, a report in the journal Nature has found a way to identify cells that are likely to have the abnormal beat, and that a combination of therapy of existing drugs can control and potentially stop the abnormality. Paleontologists on the Isle of Skye have uncovered the fossilized remains of a new species of pterosaur, the famous extinct clade of flying reptiles that lived during the age of dinosaurs. A report in the journal Vertebrate Paleontology says incomplete but 3-dimensionally preserved fossilized remains have been uncovered, including parts of the shoulder, wings, legs and backbone. Named Scioptera venzi, the fossils date back to around 168 to 166 million years ago. The discovery was quite a surprise, as most of its close relatives are from China. Cloud seeding is a type of weather modification that aims to change the amount or type of precipitation that falls from clouds by dispersing substances into the air that serve as cloud condensation makers or ice nuclei, which then alter the microphysical processes within the cloud. Whether cloud seeding is effective in producing a statistically significant increase in precipitation is still a matter of academic debate. And as Tim Mendham from Australian Skeptics points out, there are some serious concerns associated with the chemicals being used to seed the clouds.
It's an interesting thing, isn't it? It's been a big thing. Obviously, there's a need for rain in certain places. So, drought-ridden places, etc. Crops, agriculture, all that sort of stuff, they need rain. And that encourages systems to create the rain, to help the rain along, whether it's lightning rods or whether it's rain dancers or whether it's firing cannons into the air. The cloud seeding idea has a little bit more scientific basis to it. The idea that you go up into a plane and you drop little granules of various sort of chemical combinations and they form, as you do with creating a pearl, an artificial pearl, you put a grain of sand in something and the pearl builds around it. Supposedly these chemicals that are in the air, and they include sodium chloride or calcium chloride or silver iodide, depending on the cloud you're putting this into, they will sort of draw droplets to them. They'll create a drop around this grain of chemical. You have to have a cloud. You can't just do it in the open air. And I think, from my understanding of it, and it is a sort of an interesting area, but there's still a lot of mystery about it or uncertainty. You're basically pushing a cloud into raining. I don't think you can make rain out of a clear air or a cloud that's basically not going to go anywhere. And so, there might be some basis to it. The places you're cloud seeding might be going to rain anyway, perhaps not exactly there, or perhaps not exactly with the amount of rain that you might get through cloud seeding. I do know that CSIRO, the Commonwealth Scientific Industrial Research Organisation in Australia, did do a lot of studies of this. I think they came up with yes, maybe, but they did get a lot of information about what it takes. It
wasn't a water divining, was it?
No, not a water divining in that particular one.
Good.
They'd stopped. Yeah, but what someone does point out in this particular discussion of cloud seeding that came out recently was that some of the chemicals that are used can be dangerous in their own right. They can cause pollution, etc., especially when you're sort of trying to you're triggering ice production in supercooled clouds. You use silver iodide, and silver iodide...
Well, that was the most common seed element, wasn't it, usually?
Yeah, and that can be poisonous. It certainly can be polluting. So you might be getting rain, but you might be doing a lot more damage at the same time. The trouble with cloud seeding is that it does have a downside, and a serious downside to it, that you might be sort of putting more things in the air that you don't want than getting rain out, which you do want.
Simply getting the rain to fall potentially over a different area to where it was going to fall anyway.
Yeah, there were stories of conspiracies actually in the 60s or 50s where they supposedly cloud-seeded cloud in the Gulf of Mexico, and so would rain over the Gulf rather than on a Central American country that the Americans didn't want to do well, or didn't want that nation to do well. It ruined their banana crop.
Well, they probably couldn't find any poison cigars for Castro at the time.
That's right, yeah. And the other story was that China was supposedly clearing pollution out of the air by doing this cloud seeding before the Beijing Olympics.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.